3 years ago, the James Webb Telescope redefined space exploration. Now, its latest discovery, a shocking breakthrough about the origins of life and the universe, might just change everything we know. What has this marvel of modern engineering uncovered? And why is the scientific community buzzing with excitement? Join us as we dive into how the James Webb Telescope has made an impossible discovery after 3 years. On December 25, 2021, at precisely 7:20 a.m. Eastern Time Frame, an Ariane 5 rocket thundered into the skies above Europe's spaceport in Kourou, French Guiana. Its precious cargo, the James Webb Space Telescope, JWST, a marvel of human engineering and vision. After decades of anticipation, delays, and countless hours of effort, the telescope began its journey into space, carrying the aspirations of scientists and dreamers eager to unlock the mysteries of the cosmos. As the massive rocket soared into a cloudy sky, a sense of anticipation gripped the world. When the telescope separated from the Ariane 5 rocket about 30 minutes later, a wave of cheers filled the launch control room. Live views of Webb floating away, its solar array unfolding, were shared with viewers around the globe. "Go, Webb, go!" a flight controller shouted in excitement, capturing the essence of this historic moment. NASA Administrator Bill Nelson, speaking to Space.com, called the mission one of a kind, acknowledging the telescope's potential to offer breakthroughs in understanding the universe. The significance of the Webb telescope cannot be overstated. "This is the most complex thing by far that NASA has ever done," said Jonathan Gardner, Deputy Senior Project Scientist at NASA's Goddard Space Flight Center. "It is more than just a telescope. It's an instrument that will answer questions about the origins of the universe and our place within it." The Webb mission is arguably the most ambitious scientific undertaking the United States has ever attempted, with a vision that stretches to the very edges of space and time. The story of the James Webb Space Telescope began in 1989 when astronomers began discussing a successor to the Hubble Space Telescope. Even though Hubble had not yet launched, the scientific community understood the need for a new observatory to continue the exploration of the cosmos. The Hubble Space Telescope, launched in 1990, soon revealed a major flaw. Its images were blurry, caused by an imperfection in the mirror. This setback delayed the development of the next-generation telescope, as resources were diverted to fixing Hubble. Astronauts completed a spacewalk in 1993 to install corrective optics, allowing Hubble to return to its mission. However, it also meant that progress on the James Webb Space Telescope stalled for several years. In the mid-1990s, the focus shifted back to the new observatory. The scientific community agreed that the next telescope should probe the earliest stages of the universe, seeking to uncover the secrets of the first stars and galaxies that formed within the first few 100 million years after the Big Bang. This goal would require a telescope with immense power and complexity. The Webb telescope was designed to be just that, built to observe the universe in infrared light and peer further into the past than Hubble ever could. The mission faced numerous technical challenges. The telescope had to be kept extremely cold, so cold that any heat from its instruments could interfere with its observations. To achieve this, Webb would rely on a 5-layer sun shield, each layer the size of a tennis court, to block the heat from the sun, Earth, and Moon. Webb would not remain in Earth orbit like Hubble, but would instead be stationed at the Sun-Earth Lagrange point 2, L2, a location 930,000 miles away. This position would provide the telescope with an unobstructed view of the universe, shielded from the heat and light of Earth, making it an ideal place for astronomical observations. One of the biggest hurdles in Webb's design was ensuring that its enormous sun shield and primary mirror could fit into the rocket's payload fairing. Both components had to be folded into a compact configuration for launch. Once in space, they would unfold into their full size. The mirror, composed of 18 hexagonal segments made of beryllium and coated with gold, is large enough to collect light from faint objects in the universe. This mirror is approximately 21 feet wide, much larger than Hubble's single, smaller mirror. Each segment of Webb's mirror is just a fraction of the size of the entire system, but together they are capable of collecting much more light than any telescope before it. After launch, Webb would begin its journey to its final orbit at L2, where it would begin unfolding and deploying its instruments. The telescope is equipped with 4 scientific instruments: the Near-Infrared Camera, NIR-CAM, the Near-Infrared Spectrograph, NIR-SPEC, the Mid-Infrared Instrument, MIRI, and the Fine Guidance Sensor, Near-Infrared Imager, and Slitless Spectrograph. These instruments will enable Webb to study the universe in unprecedented detail. It can see objects that are 10 billion times fainter than the dimmest star visible to the naked eye, and its resolution is sharp enough to detect details the size of a penny from 24 miles away. The development of Webb was a monumental effort that took over 3 decades. The technology and engineering required to make it a reality were years ahead of anything previously attempted. But this ambitious plan came at a high cost, not just financially, but in terms of time and effort. NASA, along with its international partners, including the European Space Agency, ESA, and the Canadian Space Agency, CSA, invested countless hours to ensure everything worked perfectly. Webb had to undergo rigorous testing, including vibration and acoustic tests, to simulate the conditions it would face during launch, and vacuum testing to ensure it would function in the harsh environment of space. Despite its challenges, the mission was delayed by several years, with the most significant setback being the COVID-19 pandemic. The launch, originally slated for March 2021, was pushed to October of the same year, with a few minor delays following that. Ultimately, Webb launched in December 2021, 14 years later than originally planned. In 2023, the scientific community was buzzing with excitement when the James Webb Telescope reported detecting possible signs of life on an exoplanet called K2-18b, located over 120 light-years from Earth. This super-Earth, which is between 2 and 3 times the size of Earth, seemed like a promising candidate in the search for extraterrestrial life due to its location in the habitable zone of its star, where liquid water, a key ingredient for life as we know it, could potentially exist. But in a twist that might be a bit disappointing for many, recent research by scientists at the University of California, Riverside, UCR, has clarified that these signs were premature. The excitement stemmed from the initial discovery of carbon dioxide and methane in the atmosphere of K2-18b, a potential clue that the planet could support life. What made the finding even more thrilling was the possibility of dimethyl sulfide, DMS, being present, a molecule typically produced by oceanic phytoplankton on Earth. If DMS were confirmed, it would suggest that some form of life might be producing it on the distant exoplanet. However, the signal for DMS was weak, and the evidence was far from conclusive. Shangmin Tsai, a project scientist at the University of California, Riverside, expressed caution about the detection of DMS. The DMS signal from the Webb telescope was not very strong and only appeared under certain conditions when analyzing the data, he explained. This uncertainty led the UCR team to reanalyze the data using advanced computer models to better understand the planet's atmospheric chemistry. Their analysis suggested that the detected signal might not be DMS, but instead could result from confusion with methane, another molecule commonly found in hydrogen-rich atmospheres. Tsai and his team concluded that the Webb telescope's instruments, including NIR-ISS and NIR-SPEC, might lack the sensitivity needed to reliably distinguish between DMS and methane in such conditions. Despite this setback, the possibility of life on K2-18b has not been entirely ruled out. The research team has not given up on the search. Instead, they are continuing to observe the planet using the Webb telescope's other key instrument, the MIRY, which may provide more detailed insights into the planet's atmosphere. UCR astrobiologist Eddie Schwieterman remains hopeful, pointing out that the best biosignatures on a hydrogen-rich exoplanet might not be the same as those found on Earth. On Earth, oxygen produced by plants and bacteria is a hallmark of life. On K2-18b, DMS could be a more likely signature of biological activity. Therefore, the search for life is far from over. K218b is considered a Hycean world, a term used to describe exoplanets that have vast oceans beneath thick hydrogen-rich atmospheres. These worlds are intriguing because they offer a better chance of supporting life than more extreme exoplanets, such as those too close to their stars, where radiation would sterilize their surfaces, or those too far, where they would be frozen. With K218b in the habitable zone of its star, the conditions appear favorable for liquid water. The discovery of carbon dioxide and methane adds to the possibility that it could harbor life, but scientists acknowledge that more research is necessary. Even with the uncertainty surrounding the detection of DMS, the Webb telescope's investigation of K218b has provided valuable data. As Sai noted, why do we keep exploring the cosmos for signs of life? Imagine you're camping in Joshua Tree at night, and you hear something. Your instinct is to shine a light to see what's out there. That's what we're doing too, in a way. This sense of curiosity and discovery drives scientists to continue their search for life beyond Earth, despite the challenges and occasional disappointments along the way. The search for life on other planets is an ongoing and thrilling endeavor. The findings from Webb telescopes will play a crucial role in our understanding of how life might exist elsewhere in the universe. While K218b may not yet confirm the presence of life, its S+2D marks an important step forward in planetary exploration. As technology improves, especially with the continued use of Webb telescopes' powerful instruments, scientists remain hopeful that they will one day find clear signs of life, whether it's in the form of DMS or some other biosignature. The Webb telescopes recently unlocked a new chapter in our understanding of the universe's earliest moments, offering a breathtaking glimpse of 3 of the cosmos's first galaxies. These galaxies are being observed as they were between 400 million and 600 million years after the Big Bang, in the infancy of the 13.8-billion-year-old universe. This was a time when the universe was still in its early chaotic stages and galaxies were just beginning to form. The newly discovered galaxies, though still young and disorganized, are actively feeding on surrounding hydrogen and helium. These elements are essential for the formation of new stars, fueling the growth of these nascent galaxies. Over time, as they accumulate more material and mature, they will evolve into more structured and recognizable forms, such as spiral galaxies like our own Milky Way. This transformative process is a critical component of cosmic evolution, shedding light on how the universe's earliest structures took shape. The Webb telescopes is providing an unprecedented glimpse into this fundamental stage of development, capturing the birth and early growth of the first star systems in the universe's history. The 3 galaxies observed by Webb telescope are unlike anything we see today. They are still in the process of formation, glowing with intense activity as they start to build the stars that will later define them. Their shapeless, scattered appearance reflects their chaotic early stages, but in time, they will settle into more structured shapes. You could say that these are the first direct images of galaxy formation that we've ever seen, said Caspar Elm Heinz, the study's lead author and an astrophysicist at the Cosmic Dawn Center. This discovery is particularly significant because, until now, astronomers have only been able to observe galaxies at later stages of development. The Webb telescope is showing us the very beginning of these galaxies, offering a direct look at how stars and galaxies were born. The universe's early years were marked by a period of darkness. Around 400,000 years after the Big Bang, the universe cooled enough for neutral hydrogen atoms to form. This created a fog of opaque gas that shrouded the cosmos. It wasn't until around 1 billion years later, with the birth of the first stars, that this fog began to clear. These early stars flooded the universe with light, marking the end of the cosmic dark ages. Recent research has revealed that small dwarf galaxies formed during the first few 100 million years played a pivotal role in this process, helping to clear the fog and allow light to travel freely. The galaxies seen by JWST are believed to be part of this critical early population. These galaxies are like sparkling islands in a sea of otherwise neutral, opaque gas, said Heinz, describing the galaxies as beacons of light in an otherwise dark universe. The discovery of these early galaxies marks an extraordinary achievement for the JWST, which is continuously reshaping our understanding of the cosmos. By peering into the past, this advanced telescope allows us to witness the universe's origins, from the birth of stars to the formation of galaxies. As it continues its journey, the JWST will undoubtedly uncover even more mysteries, helping scientists unravel the deep history of our universe and its earliest galaxies. More recently, the Webb telescope turned its powerful gaze to the heart of the Cigar Galaxy, a region teeming with explosive star formation. This galaxy, known as Messier 82 M82, is an extraordinary example of a starburst galaxy where new stars are born at an incredible rate, far faster than in our own Milky Way. Situated about 12 million light-years away in the constellation Ursa Major, M82 is a cosmic laboratory that offers scientists a unique opportunity to study how stars form in extreme environments. M82's star formation rate is 10 times faster than that of the Milky Way, and its core is compact and highly turbulent. This makes it an ideal target for astronomers seeking to understand the processes behind rapid star birth and how galactic environments can shape these stellar nurseries. James Webb Telescope, with its unprecedented infrared imaging capabilities, has provided a level of detail never seen before in observations of this galaxy. The NIR cam aboard the telescope has allowed scientists to peer into the dense heart of M82, where star formation is at its most intense. Alberto Bellato, a researcher from the University of Maryland and the leader of the research team, explained that M82 has long been a subject of interest for astronomers. It has been observed by previous space telescopes such as Hubble and Spitzer, but the JWST's advanced size and resolution enable scientists to see M82 in a whole new light. With the James Webb Telescope's size and resolution, we can look at this star-forming galaxy and see all of this beautiful new detail, Bellato said in a statement. One of the biggest challenges in studying star formation is that the raw material, gas and dust, is often shrouded in darkness. These clouds of gas and dust absorb visible light, obscuring the view of the stars being born within. However, infrared light can pass through these clouds, making infrared telescopes like this one ideal for this kind of research. Using infrared observations, JWST can reveal star formation hidden deep within the galaxy. The NIR cam images taken by the team show a stunning new perspective of M82. Dark reddish-brown tendrils of dust weave their way through the bright, glowing heart of the galaxy. Small green specks in the images represent regions of iron that have remained from supernova explosions, events marking the deaths of massive stars. Red patches highlight areas where molecular hydrogen is being heated by radiation from young stars. The images offer a breathtaking view of a galaxy caught in the midst of intense transformation. One of the most remarkable discoveries from the JWST's observations was the appearance of galactic winds. These winds, which were powered by star formation and supernova explosions, stretch out from the starburst core and form intricate structures that resemble blood vessels. The NIR cam images revealed streams of gas and dust extending farther from the galaxy than scientists had previously noticed. These galactic winds play a critical role in moving elements around the galaxy, which can facilitate further star formation and influence the galaxy's overall growth. The JWST also helped scientists track the structure of these galactic winds by detecting polycyclic aromatic hydrocarbons, PAHs, which are chemical molecules that emit a distinct signal in the infrared spectrum. PAHs are known to survive in cooler regions, but are destroyed by the intense heat of star-forming areas. This allowed astronomers to study how hot and cold components within the galactic wind interact with one another. Surprisingly, the PAH emissions resembled the structure of ionized gas, which was unexpected given that PAHs are not typically stable in such strong radiation fields. It challenges our theories and shows us that further investigation is required, Bellato said. The Webb telescope's observations of M82 have opened up new avenues of inquiry, and the team is eager to continue their studies. By analyzing the light spectra from M82, scientists hope to determine the ages of the star clusters within the galaxy. This will help them understand how long each phase of star formation lasts in such an extreme environment. Moreover, the team plans to combine these new images with broader, large-scale observations of the Cigar Galaxy, as well as data from other starburst galaxies, to gain deeper insights into the processes at play. Understanding the feedback cycle in starburst galaxies, such as how winds and shock waves from young stars and supernovae remove gas and dust from the galaxy, is crucial to theories of galactic evolution. These compact starbursts were common in the early universe, and studying them can provide valuable clues about how galaxies formed and evolved over time. A detailed understanding of this feedback cycle is important for theories of how the early universe evolved, said Torsten Boker, a scientist from the European Space Agency who is part of the team. The research team's findings have been accepted for publication in the Astrophysical Journal, marking a significant step forward in our understanding of star formation in extreme environments. The JWST's ability to capture the fine details of galaxies like M82 offers a glimpse into the past, helping us unravel the mysteries of how stars, and by extension, galaxies, are born and evolve. With its unparalleled power, JWST is sure to continue pushing the boundaries of our knowledge, unlocking the secrets of the universe one observation at a time. Astronomers have made yet another groundbreaking discovery using the Webb telescope, identifying icy building blocks of life in the gas and dust surrounding two protostars. These protostars, which are still in their infancy, offer a glimpse into the early stages of star and planetary system formation. Among the molecules detected were simple ones like methane and complex organic compounds such as acetic acid and ethanol. These findings have significant implications for understanding the origins of life and the processes that shape new solar systems. Previously, scientists had theorized that complex organic molecules in icy form could exist around protostars. These theories were based on laboratory experiments on Earth and observations from earlier space telescopes. However, the detection of these ices was tentative until the advanced capabilities of the James Webb Space Telescope confirmed their presence. As part of the early release Science Ice Age program, the telescope revealed diverse ices in the darkest, coldest regions of molecular clouds. Recent observations through the James Webb Observations of Young Protostars program have now solidified these findings, specifically around the protostars IRAS 23385 and IRAS 2A. Of particular interest is the low-mass protostar, IRAS 2A, which scientists believe shares similarities with the early Sun. Around 4.6 billion years ago, the Sun was in a similar primordial stage, and the chemical ices identified around IRAS 2A were likely present in the early solar system. These ices may have been integral to the formation of Earth and the emergence of life. The research team, led by Leiden University's Will Rocha, explained that these complex organic molecules likely form through solid-phase chemical reactions on the surfaces of cold dust grains. This discovery answers a long-standing question in astrochemistry. How are complex organic molecules created in space? Their detection in icy form suggests that solid reactions, rather than gas-phase reactions, play a crucial role in their formation. Although complex organic molecules have been detected around protostars before, they were typically found in warm gas form, resulting from a process called sublimation, where ice directly transforms into gas without becoming liquid. By identifying these molecules in their solid, icy state, researchers can better understand the processes that lead to the formation of even larger molecules. These larger molecules could eventually play a role in the origins of life. The researchers are also keen to study how these molecules make their way to forming planets. In the later stages of a protostar's evolution, when it accumulates enough mass to initiate hydrogen fusion, these molecules may migrate inward toward the planet-forming regions. Scientists suggest that icy materials, which are more easily transported than gases, could be incorporated into comets during this process. When comets collide with forming planets, they might deliver these organic molecules, potentially setting the stage for life to develop. This theory aligns with the idea that comets and asteroids played a role in delivering essential molecules to the early Earth. The team identified a wide range of key molecules in the icy clouds surrounding the protostars, including acetaldehyde, ethanol, methyl formate, and acetic acid. These complex organic molecules were found alongside simpler ones like methane, sulfur dioxide, formaldehyde, and formic acid. Formic acid, for example, is the compound responsible for the sting of a bee, while sulfur dioxide, a molecule made up of sulfur and oxygen, could provide crucial clues about the conditions necessary for the formation of habitable planets. Research has suggested that sulfur-containing compounds, including sulfur dioxide, played a vital role in driving metabolic reactions on early Earth. This makes their detection in the icy environments around protostars especially exciting and could deepen our understanding of how life-supporting molecules form in space. Another exciting discovery involves the detection of negative ions in the gas and dust around these protostars. Negative ions, which are atoms with extra electrons, may contribute to the formation of salts, which are crucial for creating chemical complexity at higher temperatures. The presence of these ions suggests that the ices surrounding these protostars are more complex than previously thought, providing fertile ground for future research. These findings emphasize the importance of studying protostars and their surrounding environments to unravel the mysteries of life's origins. The detection of these icy building blocks not only highlights the incredible sensitivity of the James Webb Space Telescope, but also offers insights into how organic molecules are transported and preserved in the earliest stages of solar system development. As astronomers continue to explore these distant regions, they edge closer to understanding the cosmic processes that may have shaped life on Earth and could potentially influence the formation of life elsewhere in the universe. This journey of discovery is a testament to humanity's quest to uncover its place in the cosmos, revealing how the tiniest molecules in space can have the most profound impact on life itself.
Now that we've seen what the James Webb Space Telescope has uncovered, what do you think is out there waiting to be discovered next? Could there be even bigger revelations about the origins of life or the universe itself? Let us know your thoughts in the comments below. It's in the comments below. It's in the comments below. It's in the comments below.